Okay, thank you for the invitation. So I'm going to talk about EFTs in cosmology and in particular about the particular application of this. So in general, in cosmology, we are interested in studying very large scales, the largest possible scales in the universe. However, we are often ignorant about the macroscopic physics. So this is the situation in which effective field theory is very useful. It allows us to have a systematic, it gives us a systematic way of parameterizing our ignorance into some free coefficients and do an expansion in terms of interactions or operators that become subsequently less and less important. And usually it's enough to have a couple of those free parameters to give a good description of what we observe. So for instance, an old example is the theory of bias, when in reality we are observing the stars or galaxy in our universe. But if we are interested in the long wavelength distribution of matter, then there is a bias expansion that allows us to it's very simple. So when we talk about these galaxies, we don't know exactly what is the underlying theory of their formation. There are many unknowns about the details of how the galaxies or stars are forming, but the bias expansion allows us to parameterize that ignorance into a set of free parameters, and it's enough to keep a few of those as long as we are interested in long wavelengths physics. Now today I'm not going to talk about EFT for the largest scale structure. I'm going to talk about the effective field theory application in the context of warm inflation. So this is something that has been discussed, has not been discussed much in this context, effective field theory for warm inflation, but this is something that I've been working on recently. There has been some interest in it in recent years, and it is a perfect application of EFT, perfect example of how EFT can be applied to a problem in cosmology. So I thought it would be nice to talk about this example. So what is warm inflation? It's a model of inflation in which we have a non-zero radiation energy density, which remains approximately fixed during inflation. So this is very different from the general models of inflation that we normally talk about, in which if we start from some non-zero and radiation energy density, it dilutes away very fast. Why does it remain fixed? It's because inflaton is coupled to some other sector, and as the inflaton rolls, energy gets transferred from the inflaton into this other sector and heats up that other sector. That transfer of energy leads to an extra friction term, dissipation term in the equation of motion for the inflaton field. And then the assumption is that the requirement for this model to work is that this other sector is sufficiently strongly interacting so that this energy that is transferred thermalizes. Now, the idea of having a particle production during inflation is an old idea. Goes back to 80s. However, usually there is some problem with implementing this idea and getting warm inflation. And the problem is that having a large friction usually leads to having large back reaction on the potential. So it seems that it requires fine tuning, or it is not natural to have warm inflation. This problem recently was solved, or there was a proposal that was very nice from this perspective, because it did not suffer from this issue. And this is this model which was called minimal warm inflation by these authors. And it's based on a very simple underlying model that we are very familiar with. If we imagine that the inflaton field is an axion and it has a coupling to a non-abelian gauge theory via FF2R, so we have phi over F times FF2R, then in this model the correction to the potential will be suppressed by they come from instantaneous, and they will be exponentially suppressed if we are at weak coupling. However, if we are at finite temperature, finite and large compared to the critical temperature of this non-abelian gauge field theory, then the friction term is only parallel suppressed in the coupling parameter. So therefore, we can get a large friction while having a small correction to the potential. Okay, so this seems to be a working macroscopic model for warm inflation. Now, why do we even care about warm inflation? Why are we interested in it? There are several motivations. One, and perhaps the most important one, is that it is conceptually different from the standard models of inflation. Why? Because here the fluctuations are produced by thermal fluctuations rather than being the 0-point fluctuation. And then we also have a non-zero. Even though we have accelerated expansion, there's always something going on at sub-horizon scale. So unlike the usual situation when we expect that at sub-horizon scale during inflation, everything is cold and empty, here there are things going on, and there's non-zero energy density. There is a natural embedding of this inflation model into the thermal history. Like inflation could start after a period of radiation dominant and then end again by reheating to radiation dominance. It is very common to think of axion as a good candidate for inflaton, again because its potential, it has an approximate shift symmetry that protects its potential from getting large corrections, and axions are often coupled to gauge field theories. Finally, because of this extra friction term, we can get inflation on potentials that wouldn't allow cold inflation. Or in other words, for a given potential, in a warm inflation scenario, we'll have different prediction compared to cold inflation. For instance, here we can get predictions for NS and R, which are consistent with the current constraints with the lambda phi to the fourth potential. If we have a friction which is of order 6 times Hubble, while phi to the fourth potential is ruled out for cold inflation, phi to the fourth potential is ruled out because of predicting too much gravitational. Okay, so these are the motivation. Now let us talk about the application of effective field theory to this model. Why is effective field theory useful in this situation? It is useful because there is a hierarchy of scales. We are interested in cosmological perturbations that are frozen at the scale of when their wavelength becomes, or their momentum becomes of order of Hubble, wavelengths of order 1/Hubble. And this is a scale which is much distance scale which is much bigger than the inverse temperature, mass scale which is much smaller than temperature. And this hierarchy of scales allows us to apply the effective field theory. The relevant degrees of freedom at this scale are fluctuations of inflaton and the hydrodynamic fluctuations of the radiation fluid. So what we need to do is to describe the evolution of these fluctuations, which are given by essentially two equations. One is the inflaton equations, just a scalar field, and I'm writing here the equations at lowest order in derivatives. And then the hydrodynamic fluctuations are described by the conservation of energy momentum tensor. But again, to lowest order in derivatives, this would be an energy momentum tensor of a perfect fluid, which is this radiation fluid. Now, these two sectors are coupled to each other via this FF dual coupling that we have. Now, the right-hand side of this equation, the way I have written, is not actually consistent with what I said, because now the right-hand side contains FF2R, which knows about this Coulomb field. While in this effective description, we don't have those gluons or those non-abelian gauge fields. Those are not part of the long wavelength fluctuation. So this term that is coupling the two sectors, in this effective description, it has to be understood. It has to be studied again in this same spirit, meaning that we only care about its expectation value, which is the thing that gives us the friction term to begin with, but now I have written it in a covariant way. And then the fluctuations around that expectation value, that now we will treat it as a noise term, as a short distance noise term, which about which we only need to know the correlation functions. So this noise is something that is very short range correlated, because it is coming from the it is consists of those gauge fields that have the typical wavelengths characterized by the temperature scale. And the correlations are, we can say, interesting things about the correlations on very general grounds. So for instance, the 2-point function of this noise is completely fixed at large distances by the fluctuation dissipation theorem. So once I know what is the friction coefficient and temperature, I know what is the 2-point function of this noise. I can also say, put lower bounds on the higher order correlation functions of this noise. So for instance, with this 2-point function, one can determine the spectrum of curvature fluctuations in this theory. And it was based on this where I claimed that the NSR predictions of, say, 5 to the 4th model are within the current constraint.
2 minutes.
Okay, thanks. But perhaps more interesting is would be the predictions of the model for non-Gaussianity, in particular the 3-point function, which we often parameterize by this FNL function. So what one can see is that this model actually always predicts FNA larger than 1, but most of the time not too much larger than 1. So, which means that this model is, there is a large range of parameters of warm inflation which are not ruled out yet, but they are within the range that we are hoping to achieve in the near future. And then the source of non-Gaussianities at leading order, there are two sources that I can say a couple of words about. One is just from the Poisson statistics of the noise term. So the fact that the noise term is not perfectly Gaussian, there will be non-Gaussianities, and that will be bounded from below by something that is related to the temperature. And then the other comes just from the nonlinearities of this fluid system that we have. And that only depends on gamma. So again, here we see that in this model, just this friction coefficient completely determines the leading contribution to the non-Gaussianity, or this part of the leading contribution. And then there will be one other parameter that adds another shape of non-Gaussianity. In addition, these shapes of non-Gaussianity are rather distinct. So for those who are familiar with the squeeze limit, this 3-point functions, they are the momentum, because of conservation of momentum, they form a triangle, and then in the squeeze limit, we have behaviors that generally distinguish between different models of inflation. Now here, in this model, in various regimes, there are several regimes where one can get very distinct features in the squeeze limit of the model. Like for instance, in the regime of a small friction, one can get the squeeze behavior that is, for those who are familiar with these shapes of non-Gaussianity, is K long over K short, and this is exactly in between the local shape and equilateral shape. While when we are in the large friction regime, then there will be some period in which we have a squeeze limit that is not decaying. So this is somewhat similar to local shape, but we also have some angular dependence, quadruple angular dependence. Okay, so there are other features that I don't have time to talk about. So just to conclude, we often deal with situations in cosmology when there is a hierarchy of scales, and in those situations, effective field theory is very useful. Now I talked about one example, warm inflation. When if inflaton is an axiom, then it is natural to assume that to consider the case in which it is coupled to some gauge field theory, and this coupling can lead to via this coupling can lead to warm inflation via a mechanism which is called the Spalaron. And then this warm inflation scenario can be studied rather efficiently by effective field theory, and it leads to interesting predictions for the observables and non-Gaussian. Thank you.
Quick questions? Okay, then thank you again, and it's time to move on. Was there something online? Okay, thank you. Let's thank me again.